Thanks everyone for braving the freezing cold, and especially our speaker today, Dr. Keola Wierschem, who's currently visiting us from National Taiwan University. So he was stateside, and we grabbed him up. This might be his first blizzard. Is it your first blizzard?
Yeah, definitely my first
blizzard. So from Hawaii, and then he got his Ph.D. at Florida State University. Worked with Masukas on quantum fluids, things that I'm very interested in, and then on to Singapore at Nanyang Technological University, where he worked with Pinaki Sengupta on a lot of stuff we're going to talk about today, I guess, low-dimensional quantum magnetism. And he's currently a postdoc with a good friend and collaborator of mine, Zhao, in Taipei at National Taiwan University. So thank you very much for visiting. We've had a productive day, and Keola's going to be here tomorrow as well. So as a small token, we have a little gift for you.
Wow.
And so Keola's going to tell us about numerical studies of low-dimensional quantum magnetism.
Okay, let me open it maybe? So, okay. I could really use help. Coffee mug. Thank you. So, yeah, I've done pretty well in here. So if I speak too fast, bear with me. I'll try to breathe a little bit and slow down. So thank you for the introduction, Adrian, and I'd just like to thank the physics department for inviting me to give the colloquium while I'm stateside, as Adrian mentioned. So let me also acknowledge my postdoc advisors. So Numerical, I'm working with in National Taiwan University. So we call this NTU, and it's in Taipei. But before that, I was working with Pinaki Sengupta in Singapore, and that is also NTU. That's Nanyang Technological University. So these are the two NTUs here, and you see it's very sunny and warm and nothing like the house or side here.
You've only worked in warm places, right? Florida, those
Yes, yes. It's good to be here though. And so the outline for my talk today is basically, I'll try to give a brief overview of quantum magnetism, or at least those portions that might help understand the latter portions of my talk. And then the main concept I'm going to introduce and talk about is the Haldane conjecture. So this is for one-dimensional spin chains, and it has very interesting properties, and there are some Haldane gap materials that realize this. So I'll introduce those, and then I'll talk about the method I use to study these, and that's just quantum Monte Carlo, and it's a very useful method. And with this method, then I'll show how I can study a quasi-one-dimensional system of the quasi-1D Haldane phase. So this is a system in 3D where we have very weak coupling between chains, so it's effectively one-dimensional. But I'll study how the interactions between the chains can alter things. And then finally, I'll talk about what the nature of the quasi-1D phase is. Kind of hard to describe now, but when we get there, hopefully it will make sense. So, the brief overview. So the origin of magnetism is basically at the atomic orbital level. So here is just an illustration of the evolution of the atomic model from the plum pudding model through to the quantum mechanical model, and it's really in this electronic states around the atom that the magnetism lies. So if we have local moments, we just have the, say, electron that's orbiting about the nucleus in a quantum orbital. It also has some intrinsic spin. So there's a orbital angular momentum L and an intrinsic spin momentum, angular momentum S. And both of these can give rise to coupling to like a magnetic field. And in particular, if all the electronic angular momentum in a material aligns, you can get things like ferromagnetism. So they all can align along a single direction. And in particular, for the systems I'll study, they're more or less transition metal magnets. So the orbital momentum is actually quenched by the crystal symmetry. So basically the L becomes 0 And so the total angular momentum, which J, which is just S plus L, well, the L is 0, so we only really get the S instead. So for the metal ions that are most relevant are the copper 2 ion, which has one empty electron, one missing electron from its D shell, and that gives a spin 1/2 degree of freedom plotted here. And the nickel 2 and the vanadium, I think 3, give spin 1 because there's either 2 missing electrons or only 2 electrons in the orbital, and they just, S total is just the sum of the two. So we can get materials that have effective spin 1 and effective spin 1/2. So what happens in between the moments? So these local moments have interactions, and they can be the dipole-dipole interaction or the direct exchange, and there's also a super exchange. So the super exchange is where the electron in an orbital has an intermediate pathway to a neighboring atom, and this can give rise to the antiferromagnetic interactions if this angle of the bond is just right. So I'm mostly interested in the antiferromagnetism, so this is kind of the microscopic pathway through which the antiferromagnetism arises. So that's kind of where the magnetic moments originate within the materials. But for the models of magnetism, let me just show a quick introduction. So for the classical models, the simplest models are basically the Ising model, and then also there's the XY model and the Heisenberg model. And they're basically spin pairs that are coupled together. You could just take a dot product of the two spin vectors, and the main difference is that you have a different number of components between these models. So the Ising is the simplest. It's a one-component model, and the XY has 2 components, and Heisenberg has 3. So basically, the Ising can be up or down. The XY, you can be anywhere on a unit ring, and the Heisenberg is the spin can point on a unit sphere. And these can give rise to different textures within the materials, as illustrated in these figures here. So there's domain walls for the Ising model. That's basically the only type of boundary you can have. And for XY, there's new types of textures. The vortice, where the spin will rotate. So the direction of the spin rotates about a specific point, and that's a vortex excitation. And then there's also some skyrmion excitations possible in the Heisenberg type of spins. And so for the quantum system, basically we can have the same model, but now we have to take account that the angular momentum is now quantized. So we choose some sort of projection axis, and along that axis, the angular momentum becomes quantized. This is usually the z-axis. And if we have a spin s, the spin projection can take from minus s up to 0 and then to s. And this is because we have the commutation relations between the spin components. So the spin x, the sx, and the sy and the sc do not commute with one another. But what we can do is we can construct the raising and lowering operators. So we have the s plus and s minus defined in terms of the sx and the sy. And so the interaction, say in the Heisenberg model, if we expand out, we can replace the sx, sx, and sy interaction with the raising and lowering operators, and it just gives this simple term here, where we have a kind of spin flip up and down pair, and the converse down and up spin flipping, and then the ZZ interaction. So for the spin 1/2, the raising and lowering operator, just if you have a spin up, it flips it down. And if you have a spin down, the raising operator will just flip it back up. And for spin 1, similar thing, but now we have the spin projection 0 that's possible. So you will lower the spin up to 0, and then again down and vice versa for this raising operator. So this is how we get the quantum models. Now, I also want to mention the effect of fluctuations in low dimensions in this given example. So this is a very famous theorem, the Mermin-Wagner theorem, and basically it says that if you have a continuous symmetry, you cannot have spontaneous symmetry breaking of the symmetry in 2 or lower dimensions at a finite temperature. So to understand this kind of statement, you just can construct a very simple argument in 1 dimension. And that is, if you have like an XY spin, and you presume you have a ferromagnetic ground state where all the spins are aligned and you have long-range order, well, you can calculate the cost to slowly rotate the spins from one to the next as you go along some distance L. And after you rotate it all about in a unit circle over some distance L, you can calculate the energy that costs. And the Hamiltonian, or the energy cost, is basically proportional to the cosine of the angle between the neighboring spins. And so you can show that the energy of this type of spin wave excitation is proportional to 1 over L. So as L grows, this energy cost decays. Whereas for the entropy is like log L, because there are L different ways we can form this type of excitation, where the spin up can point anywhere, this spin up spin can be anywhere along this length. So if this is the scaling of the energy and that's the scaling of the entropy, we can calculate the free energy to see which state will be the equilibrium state. And for a large enough L, the log L term is guaranteed to be dominating. So basically the entropy will dominate at any finite temperature. So another way of stating that is that at any finite temperature you can find a length L where the spin excitation along that length is energetically preferred over any magnetically ordered ground state. And this also, the same thing kind of holds in 2 dimensions, and but the main point is that in low dimensions the fluctuations are much stronger and interesting things can happen that don't happen in 3 dimensions. So another example of what can happen is given by the Haldane conjecture. So basically, the Haldane phase in 1 dimension. So the Haldane conjecture is for a spin S Heisenberg magnet in 1 dimension. So this is a chain. So I have the interaction between the site I and its neighbor I plus 1, sum over I. So I have a chain. This is only along 1 dimension that we have these interactions. And the Haldane conjecture just says that for the spin S Heisenberg antiferromagnetic, the antiferromagnet, the ground state will be gapless if the spin S is half-odd integer. So spin 1/2 or spin 3/2 and so forth. Whereas if it's an integer spin, the ground state is gapped. So it's a very distinct difference between integer spin and half-odd integer spin. And this is quite astonishing, and at the time it was a pretty radical idea derived from field theory, and but it was very quickly backed up by numeric investigation. So the easiest way to see it now is to just plot the dispersion for a spin 1/2 chain, and which is from the beta ansatz is gapless, and the lowest excitation behaves like this, and compare it to the spin 1, where it's gapped for 0 momentum excitation, and it remains gapped all the way through to pi, where the lowest excitation to exist, and this excitation here is the so-called Haldane gap, because that's the minimum gap in the system. And this persists also for spin 2 and so forth, but the value of the gap decays exponentially with the spin size. So as we approach the classical Heisenberg antiferromagnet, where S goes to infinity, the gap actually goes to 0 again, and we get the correct value for the classical ground 0 temperature state. Okay, so the spin 1 has the most robust gap, so that's the system I'm going to study. And so the spin 1 Heisenberg antiferromagnetic chain, here's the nearest neighbor, just spin exchange interactions again. These are isotropic, but we can add another term that's the single ion anisotropy, and this is only relevant for spin 1 or greater. And this basically, if you think, if we're projecting along the z-axis, this adds an energy cost to be spin up or down when d is positive, whereas the spin 0 is relatively less energetically costly, and the opposite is true when d is negative. So in the large positive d limit, we basically will get only spin 0 on each side. So it's just kind of this state here, this phase at large d, is adiabatically connected to just a product state of 0 spin on each site. Whereas when d is negative, instead the up and the down spin are energetically preferred, and we just get the nil state, which is Ising antiferromagnetic order. And in between is where the Haldane phase lies. And the most interesting thing is that this Haldane phase and this large d phase are in some ways the same phase because neither breaks any spontaneous symmetry. So they're both symmetric. They have all the symmetries of the Hamiltonian, but somehow they're distinct phases because there's a phase transition between the two. So this is kind of odd. And in order to investigate the Haldane phase a little bit more closely, we can look at an exact solution for a related model, the so-called AKLT chain. This is after Affleck, Kennedy, Lee, and Tasaki. And they showed that if you add a bi-quadratic term, which is just si.sj quantity square, then this particular Hamiltonian with the weights between the bilinear and biquadratic term is a sum over projection operators, Pij. And the Pij is just a projection onto spin 2. So basically, it's a fancy way to write the Hamiltonian in a simple form. And when you have a Hamiltonian that consists of projection operators, you can find a ground state simply by finding a state that has 0 projection onto the space that this projection operator projects onto. So that's kind of maybe tricky mathematically to show, but basically in this case we can write a state by hand that has 0 spin projection onto the spin 2 space. So how do we do that? Well, we take each spin 1, which is represented here by this red circle, and say that it can be thought of as consisting of 2 spin 1/2 degrees of freedom within it. So these are the 2 small blue dots here, and those 2 spin 1/2 degrees of freedom, we just do a symmetric combination, and that gives you the spin 1 degree of freedom total. And so we just, this red circle just says we're projecting the 2 spin 1/2 degrees of freedom inside onto the spin 1 space. And then all we have to do is say that the neighboring spin 1/2s between 2 neighboring sites, just say, imagine they form a singlet. So this is a singlet, this is a singlet, these are all singlets. Well, if these 2 spin 1/2s are in a singlet here, then if I look at the spin projection onto spin 2 space at this bond, that has to be less than it has to be 0, because no matter what state that this spin 1/2 or this spin 1/2 is, these 2 spin 1/2s add up to 0. So I can't have the other 2 add up to anything greater than 1. So that's how you can see that the spin projection onto spin 2 is 0, and thus this is the ground state of the parent Hamiltonian. And the most interesting thing about this wave function is that if you take an open chain and look at the edges, there are these unpaired spin 1/2s. So these spin 1/2s are basically free. In a finite chain, they might have some very weak interaction between each other, but as this chain goes to infinite, or to the thermodynamic limit, these spin 1/2s at the edge are identically free, and they give rise to a 4-fold degeneracy of the ground state. So these spin 1/2s at the edge are very interesting, and kind of a characteristic of the Haldane phase, because if we take this Hamiltonian and we slowly vary this term and take this factor from 1/6 all the way down to 0, there's no phase transition. This state here is actually adiabatically connected to the Haldane phase. So the properties of this state are more or less going to hold within the Haldane phase. Now, another way to kind of characterize this state is to apply a non-local unitary transformation. So this was introduced by Kennedy and Tasaki and also by Ashikawa. And basically, it's some mathematical transformation where you transform the original Hamiltonian into another Hamiltonian that's local. And the details of the transformation aren't too important. The main idea is that in the transform system, the equivalent phase to the Haldane phase breaks a symmetry explicitly. So basically, we know that the Haldane phase breaks a hidden symmetry, which happens to be the Z2 cross Z2. This is a dihedral symmetry of rotation about 2 orthogonal axes by pi. So it breaks a hidden symmetry. So there is an order in the Haldane phase. It's just not an order you can see with any local correlation functions. Yes?
So in the Haldane phase, if you ignore the spin zeros, it's always up, down, up, down, up, down, up, down? Or can you get 2 ups in sequence?
Okay, so yeah, so basically, like you've seen, this transformation is the equivalent of removing the zeros from your state. And if we look at this wave function, the AKLT wave function, that one will actually be exactly ordered in this fashion. So for the AKLT point, the resulting order is precisely nil, and so this up, down is exact. In the Haldane phase, there's actually fluctuations about that, so you could have some up, spin patterns here, but that's just a quantum fluctuation away from the ideally ordered case. So it still has this type of order, just reduced by fluctuations. Okay, so the way to measure this type of ordering, which is a non-local order, is to use what's called a string correlation function, or measure the string order. So basically, here, this is just the regular correlation function for nail order. It's just, we look at the spin correlation between the z component at site I and the z component of spin at site j. But for the string order, instead of just SIZ and SJZ, there's some non-local term here that depends on all the spins between the two. So it's basically this e to the I pi and then the sum of all these SKZ. It basically measures what's the total sum of these spins between them, and then creates a phase factor out of that. So basically, if you have this type of non-local order here, then it will give you phase factor 1. Otherwise, it'll give you some other phase factor that will scramble the order. And the main point is we can find this string order, and it's much more long range in a finite system than the nail. And indeed, if we go to the thermodynamic limit, the string order will be finite, whereas the nail order will go to 0 for the infinite size system. So the string order for the 1D Haldane chain actually captures the properties of this phase very well, and it's completely distinct from the large D phase, because if we measure string order in the large D phase, it is 0. It's just not present. So now I'll just briefly mention that there are Haldane materials. So there's spin 1 compounds that have a Haldane gap that's been measured, and many of them, such as NEMP and NDMAP and this, I don't know how to say it, but this silver, vanadium, phosphorus sulfide, or not sulfur. There are many spin 1 compounds that have a Haldane gap, and no ordering transition has been measured in them. And most of them are nearly ideal spin chains, but in any material, there's going to be some finite interchain coupling present. So that's something to consider. So one question is, how does the finite coupling affect the Haldane physics? Is it still adequately described by just the 1D theory? And to really answer this question, we need to study fully 3D systems that have weak interactions between chains and just see what happens. And to look at this quasi-1D limit, quantum Monte Carlo is a very suitable choice because we can handle 3 dimensions at finite temperature very accurately and just take the limit that the interchain interactions are very weak, and also we can extrapolate to 0 temperature. So now I just want to briefly overview the quantum Monte Carlo method. So I'll focus on a specific one that's a specific implementation called stochastic series expansion, and it's how we can get loop updates for this that make it very efficient. Okay, so what is quantum Monte Carlo? Well, it's an exact method within statistical uncertainty, so I'm not making any approximations, and it can deal with finite temperatures and system sizes, and it allows us to extrapolate to ground state results in the thermodynamic limit, which is basically what we want to do for comparison to real materials. And basically the idea of quantum Monte Carlo is to map a quantum problem onto a classical problem in d+1 dimensions. So you get an extra dimension called imaginary time that deals with quantum fluctuations. And so basically the real problem to solve is if we have the observable in quantum statistical mechanics, we have to take the trace of the observable multiplied by this density operator e to the minus beta h, where h is a Hamiltonian that is can have off-diagonal quantities. It's basically how to deal with this exponent of an operator. It's not easy to do unless we have the eigenstates, but it's not easy to get the eigenstates, so instead we want another way to proceed. So for the stochastic series expansion, the main idea is to say, well, let's take this exponential and expand it as a Taylor series. So that's pretty simple to do, but this has to go from 0 to infinity. So what we do next is we take advantage of writing the Hamiltonian as a sum of bond terms, because as long as we only have two spin interactions, then we can rewrite the Hamiltonian in terms of bond operators. And then the power of the Hamiltonian, h to the n, just becomes a product of bond operators summed over some configuration of those bond operators. So it's kind of hard to see here in this equation, but basically what we do is we have some bond interaction operator here represented by the rectangle, and it can operate on different bonds, meaning pairs of spins, and we have some particular configuration. And basically what we need to do with Monte Carlo, or quantum Monte Carlo, is to sample over all possible orders of these bond operators and all possible orders of the expansion n. So if this expansion has to go from 0 to infinity, that seems like it would really kill us. But luckily there's this factorial term, and if we plot out the actual n in our simulation, it's peaked over at a specific value, and the width of the peak is quite narrow. So this peak is at 4,800, but the width here is only about 200, or the half width is 200. So it's very narrowly peaked. So in some of our production runs, we'll go up to 1 million or even 2 million n equal to, for the order of the expansion operator, n for this value n. But it's really narrowly peaked, so we don't have to do 1 million different configurations. We just have to do many configurations with n close to 1 million. And so this is an illustration of this operator string, and for simplicity, the upspins are represented by a red dot and the downspins by an open dot, open blue dot. And these open rectangles are the diagonal terms of the Hamiltonian spin interactions, just the SC term. This doesn't change the state, but these closed rectangles represent the S plus, S minus type operations. And these are the off-diagonal operations, because if you remember, these are spin flip operations. So whenever we have this black rectangle, it's going to flip this spin up and make it a down, and flip this down spin up and make it an up. So basically, we can, once we have the operator string with these bond operators in it, we can replace it by just a map where we only include these so-called vertices, or these bond operators. And once we have this kind of mapping, we can form loop updates where we just take one spin here and flip it. And then we can propagate that flip throughout the whole operator string and generate a new configuration. So in this case, if we flip this to from red to blue, it will propagate to here, and then we could perhaps go through here and make this also blue, and keep making these blue, make it blue, and then come back to the same spin. And basically we've generated a new configuration of the bond operators, and this type of update can very efficiently simulate this this expansion. So we can expand and just sample the imports and configurations, and it allows us to study these quantum models. So now I'll just talk about the quasi-1D Haldane phase. So the model is given here. So I still have these two spin interactions, but now I'm separating it into the intrachain coupling, which is along the single chain direction here, and an interchain coupling. So this is represented by J, and the interchain coupling is represented by J prime. So this J prime can take a different value, and we just take the limit that J prime over J is quite small. And that will give us basically spin chains that are weakly coupled by this J prime term. And we still have this single ion anisotropy. So this anisotropy is in spin space, and these interactions are isotropic in spin space. But the key point is we have these spatially anisotropic interactions in real space. So this J and J prime are different in real space.
Good question. So the intuition is, am I right, say, when J prime is small, so it's many chains that the gap are coupled, right? So the gap should persist, one doesn't expect any ordering or anything like that. So,
yeah, exactly.
So it should be a gap system, but maybe with some additional funky string correlations or something like that, is it right? Or
that's basically right. So the gap does persist. It takes a finite value of this coupling J prime to close the gap.
Right.
And
so what is the question one wants to ask then?
Well, as far as the string order, actually we cannot define the string order in higher dimensions than 1. So as soon as we have a coupling between the chains, the string order ceases to describe the ground state, because we're going to have correlations between the spin chains, and that just destroys any remnant of string order, and we just can't, at least there hasn't been a global like correlation function, even a non-local correlation function, that it can capture what type of hidden order is present. So we need another way to look at that. So yeah, so indeed the Haldane phase remains there basically in some form. There's a gapped ground state, and until some critical coupling J prime critical is reached. And at that point the gap closes, and it transitions to a long-range antiferromagnetic ground state. So we can calculate the value of that critical coupling, and some early results were from chain mean field theory, and they just got that some quantity n, which here is just the coordination number of chains, like how many neighbors does each chain have, times the critical coupling should be about this 0.051, and that's from the chain mean field theory, and it's kind of like an upper bound of what it should be. But later, quantum Monte Carlo simulations were done for the two-dimensional case, and they are, I guess this is a lower bound, And for the 2D case, the equivalent value is quite a bit over this. So it's interesting to calculate what is the actual critical coupling for the 3D system with the quasi-1D limit. So this is what we can do here. And so basically down here on the x-axis at y equal to 0, we have the 1D chain. And we know there's a transition here and here. So there's a Haldane phase in small d, and then at large d there's a quantum paramagnet, or large d phase. And at the other end is the nail or Ising AFM phase. But now we can calculate what the critical gap is at each value of d. And at the origin, I get something like 0.01625. And indeed, you know, it's kind of, if I calculate this, it kind of matches these. It lies somewhere between the mean field result and the 2D results. But now that I have the phase diagram at different values of d, I can plot some Haldane materials that have been studied and their parameters have been extracted through different measurements. And most of them are clustered down here near the origin, so they have very, very weak interchain interactions, but maybe some different varying degrees of anisotropy. But there are two in particular up here that are quite interesting because they lie so close to the space boundary. And these are the nickel vanidates, lead and strontium nickel vanadate. And indeed, I believe the strontium nickel vanadate, which is the closest to the phase transition, was initially thought to order magnetically. But recent studies have shown that for really pure single crystals, it does not have any magnetic ordering transition. So these are interesting to study now because if we could potentially dope or add pressure, they might induce a quantum phase transition from the Haldane over into the Ising AFM. So that's one thing that such a phase diagram can tell us. You know, so if we just plot the mean field phase diagram, these might not even be located in the right phase. But something else we can ask is, okay, so we know that this critical coupling exists, and we assume that the gap remains finite until the critical coupling, but let's look at that to just verify that the gap does remain open. So to do so, well, in 1D, they have very accurate calculation of this Haldane gap across the varying momentum, but in higher dimension, it's not quite as easy to get. So what I used was a estimator. It's just 2 times the structure factor divided by the susceptibility. So this is, strictly speaking, this is an upper bound. But in fact, if we can describe the excitations by a single mode approximation, this becomes exact. And so what you can see from the 1D case is that when k is equal to pi, the excitation spectrum is very sharply peaked here. And then there's another gap, and then there's some higher order excitations above that extra gap. So this is very close to a single mode. And so this approximation should hold very closely to the real value. So keeping the momentum k is equal to pi, that is the momentum along the string direction, I can plot across from pi through the symmetry points. And what's happening as the interchain coupling is increased is that the gap is just consistently closing here at pi. And this is because we are approaching a magnetically ordered state where the gap will actually close and we will get a linear dispersion at pi. And indeed, we're getting very close to that. Now, as this gap gets smaller, the approximation starts to break down a little bit, so I can't show the exact closing. But the trend is very clear, and that tells us that indeed the generic properties of this state are exactly as we expected. It's gapped, it remains gapped to a critical coupling where the gap closes. But is it still this type of, do we still have some sort of non-local order in this state? So, yeah, so the gap is robust and the correlations are short range, there's no spontaneous symmetry breaking, but what about the string order? So as I mentioned, you can only measure string order along a single chain. It doesn't extrapolate to higher dimensional systems at all. And actually, if you measure it along a single chain, it should exponentially go to 0. So it's really not, it can't really, we can't say that this real 3D system has string order. So we have to find another way to define it. And to do so, well, that's the last portion of this talk, is to describe the nature of this quasi-1D Haldane phase. So I have to talk about symmetry-protected topological order, which is a new concept for types of phases that don't break any symmetries but are still distinct from one another. And then I'll show that there's a new strange correlator, a so-called strange correlator, that can indeed tell us if the Haldane phase in quasi-1D belongs to this class of states. So for the SPT states, as they're often called, the symmetry-protected topological states, to understand what they are, first we should think about the classification of matter. So for short-range entanglement, which is basically any normal state that's not a quantum spin liquid or a quantum Hall state, we will have short-range entanglement. So the entanglement is finite, and there are different types of phases possible. So if there's no symmetry present, actually all the short-range entangled phases are identical. They're all the same. But with symmetry, there's the possibility for symmetry breaking. So this is the normal type of phases in matter. Water is the liquid form. There's water, the liquid form. There's ice, the solid form. And there's vapor, the gaseous form. These all kind of break a different type of symmetry or have an order parameter. But now, in the new symmetry-protected topological characterization, there's a new possibility where you have symmetry and you have symmetric states, but they can still be distinct symmetric states. So this is kind of schematically shown here for some different tuning parameters. You can have different symmetry-broken states, but you can also have symmetric states that are distinct, meaning they have a phase transition between them. And how can you understand that? Well, they're actually the same state if you break the symmetry explicitly. But if you conserve the symmetry, there'll be a phase transition between them. So the properties of them are as follows. Okay, so they're short-range entangled. They don't spontaneously break any symmetry, but in addition, they cannot be smoothly deformed into one another if we protect a certain symmetry. So that means you either have to have a phase transition or the gap has to close, the bulk gap. Now, if the symmetry is broken, then all these SPT states are just equivalent product states. And often the case is that these SPTs, we can have non-trivial properties where they'll have gapless or degenerate edge states that are topologically protected, meaning they'll always be there unless you break the symmetry. But the key point is the bulk is not topologically ordered because it's only short-range entangled. So basically you can have fractionalized excitations at the edge, but the excitations within the bulk of the material remain non-fractionalized. And a more widely known case is for the topological insulators. So they're basically the free fermion version of the SPT states. And for example, the time reversal protected topological insulators just have this Z2 protection. But here I'm only going to talk about the bosonic version. So how do you detect if you have a SPT state? Well, if you have a symmetric phase, then it is basically SPT, but some SPTs are just trivial. They don't have any fractionalized excitation at the boundary. They don't have any interesting properties compared to the non-trivial cases. So how do you say you have a phase that's separate from that trivial phase? Well, for the 1D case, we can construct a string order. And indeed, we did this for the Haldane and the AKLT states. But there's also edge states that you can look at, and these are the spin 1/2 degrees of freedom at the edge of the Haldane or the AKLT chain. And you can also look for a direct phase transition between the putative SPT state and a trivial product state. And in the Haldane phase has this direct transition between itself and the large D phase. And also you can look at the entanglement spectrum, and the Haldane phase has like a double degeneracy there. So basically, this shows that the Haldane phase is a non-trivial SPT state by all these measures. So that's in one dimension. But what happens for the quasi-1D Haldane state? Is it still a non-trivial SPT state? So to gain insight, you might just consider the spin S chain. Okay, so it's interesting to see that, okay, we know that the spin 1 chain, the Haldane phase, is non-trivial. But if you go to spin 2, it actually goes back to being a trivial ground state. And it has this even-odd effect for all integer spin S. So the odd integer spin S chains are non-trivial SPT states, and the even spin S chains are just trivial. They can be written as a product state. And a similar kind of classification exists for spin 1 ladders. So if we couple spin 1 chains into like a 2-leg ladder or a 3-leg ladder, they have a similar even-odd property. So the even leg ladders are trivial, and the odd leg spin 1 ladders are non-trivial. So we have this even-odd effect where it's trivial, non-trivial as we add an extra spin chain. But what happens is we go to the system with infinite legs, which is basically the square lattice of spin chains that are weakly coupled, or even go to 3D. So the way to maybe look at that is, the way to detect SPTs in higher dimensions is to look either at the edge states, but they're not always present in SPT, non-trivial SPT states, or we can also look at the entanglement spectrum, which should have a double degeneracy, but it's very difficult to measure this in higher dimensions than 1. And also, in order to calculate this entanglement spectrum, you might have to break a protecting symmetry. That is, you have to make a cut to break the system into 2 subregions to measure the entanglement. And that might actually break one of the protecting symmetries. So actually a new proposal is called a strange correlator, and it's very easy to measure, and it doesn't make any cuts to the system, so it should work for any type of protecting symmetry. So I'll just define that now. And okay, so it's kind of a weird correlation to measure, because it's not an expectation value. It's this kind of mixed correlator. So we have 2 different states at the edge here, where usually for a expectation value you just have the same on either side. So here this omega is a trivial product state, and this phi is a putative SPT phase, that is a non-trivial SPT state. And this O here is just some local operator that we can define locally. And if the following conditions are satisfied, that this operator is 0 in both the putative SPT state and the trivial state, and additionally that we have at least some finite overlap of these 2 states for finite system sizes, then this correlator will actually be long ranged in 1 dimension, which is quite spectacular because no correlation function for locally interacting systems should have long-range order in 1 dimension. So the physical interpretation of how this comes about is that the strange correlator is just a correlation function that's measured at the temporal boundary, that means the time boundary, right, of 2 time-evolved quantum field theories. So basically, we evolve a state from -infinity to 0 and get the ground state for one field theory, and do the opposite from infinity to 0 to get the trivial state. And the correlation function at this time equal to 0 boundary, and the spatial correlation function can be mapped through a Lorentz transformation onto a spatial boundary, and there will be a space-time correlation function at the spatial boundary. So basically, this spatial boundary should have gapless modes between the trivial and non-trivial SPT states. And somehow, when we do the rotation, this boundary retains that kind of gapless mode. And that's kind of how the strange correlator gives rise to these long-range correlations in one dimension. So the way I think of it is that we can plot out the dimension of the system and the dimension of the boundary, and then think about the possible gapless or degenerate boundary states that can exist at that boundary. And 1D, there's only one possibility, because we just have a free particle that's evolving in time. If we add any kind of field to that particle, it will no longer be degenerate. So basically, it has to have long-range order in time, because the time evolution will be a steady state. So in 1D, that's the only possibility, and we're going to get long-range order. When we go to 2D, we can have a quantum chain at the boundary, and basically this can either get a broken symmetry state if we have something like the Ising model at that boundary, and that gives rise to long-range order, or we can have a critical state which will be gapless and have quasi-long-range order. This is like at a phase transition, you have the gap goes to 0 and you get critical behavior. So in 2D you can have long-range order or quasi-long-range order for the strange correlator. And then finally for 3D, in addition to those two possibilities, you could even have a topological state, that is a long-range entangled state at the 2D boundary. So this gives rise to the possibility that this strange correlator might actually be short range. But at least in 1D and 2D, we're always going to get a strange correlator that's long range or quasi-long range ordered. And thus we can rely on it to diagnose the non-trivial SPT states. And also for 3D, if we see a long-range or quasi-long-range strange correlator, that's still evidence of a non-trivial SPT state. And in fact, it is quite rare to have a topological boundary. So here I'm just showing the result for the strange correlator in a quasi-1D system where this should be J prime. The interchain coupling is 0.01. So this is in the when the single ion anisotropy is 0, I'm in the Haldane phase, and when it's 2, I'm in the quantum paramagnetic phase. And you can see that the strange order behaves very differently in these two cases. So in the trivial case, it's going exponentially to 0, just like the Néel order and then any other measure we can throw in there. But in the Haldane, the quasi-1D Haldane phase, the Néel order is going to 0 very quickly, but the strange order is approaching some constant value as I go to the thermodynamic limit and have infinite system size. So this is telling us that the strange correlator has long-range order in the quasi-1D Haldane phase. So indeed, there's strange order in 2D. So yeah, so this is for 2 dimensions, and I also can show the same thing in higher dimensions. So you have 2D and 3D system here, and in both cases the strange correlator in the Haldane phase is going to a constant value or approaching a constant value, whereas in the quantum paramagnetic phase it's going to 0. So also in the 3D version of the quasi-1D Haldane state, I think this is saying that you have long-range strange correlation, and the quasi-1D Haldane phase really is a SPT phase, a non-trivial SPT phase. So what type of edge states could we expect for this phase? Well, I think the way to visualize this is just to stack AKLT chains on top of one another. So if you remember, this is the spin 1. These are the singlet between two neighboring spin 1/2 components. And at the boundary, there's these free spin 1/2s. And if we couple these chains weakly together, then at this boundary we can expect that we'll have a gapless spin s equal to 1/2 chain that will have gapless modes here. So I think that's probably the type of boundary excitation if we had the perfect system set up that we could measure. Okay, so with that, I'll just conclude. And I think that Haldane's conjecture showed an early insight into the low-dimensional physics that can occur that arises out of fluctuations and interesting quantum properties. Now, the Haldane phase in 1D is actually an early example of a non-trivial SPT state. Likewise, the phase diagram of the quasi-1D model is well understood, and there are materials that kind of fall into this phase diagram that are understood. And the low-lying dispersion shows the expected qualitative behavior, that the Haldane gap remains open until some finite interchain coupling is reached, and then it closes at this AFM ordering wave vector. But finally, the long-range strange correlator does provide evidence, the first direct evidence that I'm aware of, that the quasi-1D Haldane phase is also a non-trivial SPT order. So thank you very much for your attention.
Time for a few questions.
Yes.
You showed the domain walls in the icing model and the vortices in the 2D model. And then you had something, a skyrimion?
Yeah, that was just, the skyrimion is like an illustration of what kind of like excitation can occur for when you have the full three-dimensional rotation of the spin available.
So with a vortex, you can quantify that as, you know, a curl of a vector field or something. How do you identify that type of excitation as opposed to just a random assembly of local spins? Like, is there a mathematical description? Is there some characteristic?
Yeah, I don't directly know what it is, but yeah, for the skyrimion, I think you can map that system where the spins out here are spin down, and then as you go to the middle, you get a spin up. If you map that onto a sphere, basically all the spins are pointing out on top of the sphere. So I think there's some sort of topological invariant that's involved there, but I don't know the mathematical formulation.
Okay, thanks.
I just had a quick question about the physical interpretation table, because I saw that in the dimension rows, there was 0, 1, 1, 1, 2, 1. Is that second number a single time dimension, or what was that?
Yeah, exactly. So this is the extra dimension from the quantum. So the quantum system is like a classical system in d+1 dimensions.
Right.
So this is the quantum system in 1 dimension. So it's 1 spatial and 1 time. And yeah, so this is the time dimension, basically.
All right. Thank you.
Sure.
Other questions?
Right? Okay. Two very quick questions. So the first one about I don't understand, of course, deeply the topological nature and so on, but just namely, so the Haldane chain has some topological structure, and that it's also related to its degeneracy, right? So there is a degeneracy of the grounds.
Yes,
Right.
that's true.
So then, isn't it true, namely speaking, that if I start coupling these, the degeneracy somehow is gone, and then one would have something topologically trivial? You seem to say that that's not the case, though.
Well,
right?
the key to remember is that you can still have non-trivial topological, symmetry-protected topological order without the degenerate edge state. So, so the Haldane chain, if we think about the spin 1/2 at the edge, that topological degeneracy is actually protected by the time reversals.
Okay, I got it. So it's too naive, that argument that I'm saying, yeah, so that's one thing. So the second question is that, so people often say, in some effective way, that the spin ladder, it's isomorphic equivalent to Haldane chain, but not topologically, right? So if I spin 1/2 ladder, so if I take spin 1/2 ladder, so two chains coupled to spin 1/2, it's always gapped, it has effective spin ones on the runs, that interact quickly or strongly, it doesn't matter, it's always gapped.
Yes.
For any value of the run. But that is topologically trivial, is it right? Or,
I
I don't
think
really know.
the spin 1/2 ladder on the parameters can be either trivial or non-trivial.
Oh, it can be? Oh, okay.
Yeah, I think, so kind of.
It always has a gap though, right? It is gap for any value.
So if
of
the rung coupling is strong, then you just have singlets on the rung in its trivial state. But in the limit that the rung coupling is, well, I guess if the rung coupling was ferromagnetic, then it maps onto spin
but
1.
that's different, yeah.
And you will have, basically, I think if you count like valence bond cuts, you'll get like an odd number of valence bonds.
But if it's antiferromagnetic, which is usually the case in
Yes,
materials,
yes.
then it's always trivial. You would say.
Yeah, I would say that's correct. Yes.
So experimentally, how would you look for the states? Would it be looking at some D to D transition in these systems, or what exactly are, how would we look for them? Other than probably measuring magnetization, right?
Yeah, so I'm not sure for the like optical excitations what the case would be, but I think one thing that can be looked at is like the doping of non-magnetic impurities into the chain, and there's been some evidence for the if we dope non-magnetic impurities to cut the chains, that can give rise to spin 1/2 degrees of freedom in the material, and so something similar might be able to kind of distinguish whether there's actually coupling between the chains that gives rise to this higher dimensional SPP order. But I don't know about any from an excitation point of view.
Coupling between the chains is actually very weak to use the next phase, right? I mean, what I'm saying is that J prime over J critical is like 0.0 something, right? Even though a lot of it's true for a lot of materials, it seems.
Yes.
It's still, one can easily break this Haldane.
Yeah, but at the same time, I believe for a result of the small coupling, as you mentioned, I can just show it. So the small coupling here, it's like 0.01 or even 0.016 at the most. For such a small coupling between the chains, if you look within a single chain, the string order will go to 0, but the correlation length can be quite large, like on the order of 1,000 angstroms. So it's not exactly clear how you kind of get rid of that portion of the 1D type of order. So as long as you look at the chain on a scale smaller than that, it will look like a pure 1D chain. So it's only when you look at really long chains that you can kind of see that it might not follow exactly the 1D physics.
Dennis?
The original Haldane argument considered the continuum limit of the chain and found that there was an additional topological term, a Wierschem term. If you do that in 2D, is there an argument, a continuum limit type of argument in 2D, where you can see that there is this sharp transition at some critical J prime and not some smooth crossover?
There might be, but I don't really know the field theory aspect of that. I'll have to say.
You mentioned the entanglement spectrum. Is that related to the entanglement entropy? What is the entanglement spectrum?
Yeah, so...
is it not related to the entanglement entropy?
So I didn't define the entanglement spectrum, but generally if we take the reduced density matrix by tracing out some subsystem, so we take the subsystem trace of the density matrix. If we equate this reduced density matrix to a density operator e to the minus h A, which is the entanglement Hamiltonian, we can get the spectrum of this Hamiltonian, and that's the entanglement spectrum. So basically we get the reduced density matrix and then say that this is just the density matrix of a different Hamiltonian and look at the excitation spectrum of that entanglement Hamiltonian.
Okay.
So whereas, like the log rho
right
or something like that is the entanglement entropy.
Okay. And so what is the signature of the topological order in the
Okay, so
entanglement spectrum?
here it's plotted out. So Pullman, Turner, Berg, and Keola have shown this. In the Haldane phase, every single portion of the entanglement spectrum has double degeneracy or higher. Whereas in the trivial large D phase or the Ising AFM Cornell state, there'll be some mixture of some different types of degenerate or non-degenerate.
Okay.
Yes.
Sure.
All right. Let's thank Keola again for bringing us back.